So our first application is going to be finding what are called extrema, the fancy math speak for the maximum and minimum values of a function. And this is something that has applications in just an enormous variety of fields. Business people, they want to know how to minimize costs and maximize revenue. Science and engineering applications, you want to know when the temperature of an experiment is at its maximum. You want to know what the maximum load on a new material is, for example. Lots of applications of this. So before we can get into the calculus bit, we need to revisit some definitions from college algebra. We need to know specifically what it means for a function to have an absolute maximum or minimum at a certain point. Okay, so here's how the definition works. First, let f be a function with domain D. We need to know what that domain is. Then f has an absolute maximum of m. So they think that's the function value, that's the y value. At a point C, if the absolute value of, if f of x is less than or equal to that maximum for every x in D. All right, in other words, if you pick any number out of the domain, any one you want, and evaluate the function at that value, you get something less than or equal to m, that maximum. Okay, an absolute minimum, it kind of works exactly the way you'd expect. It's just the reverse, right? Lowercase m is an absolute minimum if at every x in the domain, f of x is greater than or equal to that m. So in other words, that m is the lowest value of the function. All right, so let's look at an example. And what I've done over it is it's the same function. Right? F of x equals x squared, an old classic, right, parabola. And what I want to do is I really want to emphasize the importance of focusing on what the domain is. Right? So I have several different domains here for us to consider. Right? So first is kind of that maximal domain. It's all real numbers. Right? With this domain, what are the maximum and minimum values? Well, let's add that to my table here, maximum and minimum. Okay, there is no maximum. To see this, pick any number, pick any functional value you would like to be our contender to be the maximum value. Let's say I pick 4 over here. It's kind of hard to see. Let's say I pick 1. Okay, that cannot be the maximum because if I pick this x value here, just a little bit further over, that function value is greater than that one. And if you were thinking this point might be potentially our maximum, well, go a little further over, and the function value here would be way up here. My scale's a little off. Would be way up here at 4. That value is bigger. So there is no biggest value here. All you have to do is go a little further to the right, and you're going to get a bigger result. Okay, now there is a minimum, right? There is a minimum. The minimum value of this function is 0. Right? It's this point right here, right? And to see this, pick any other point you want on the graph, right? Take a point over here. Let's say x equals 1, which gives us y equals 1. My candidate for a minimum is lower than this. Excellent. That's what we needed for a minimum, right? So in this case, there is no maximum, and there is a minimum. The minimum is 0. Okay, so how about my next one here? How about if I restrict the domain to 0, the numbers from 0 to 2, and I'm going to include 0 and 2. It's a closed interval, right? So I'm going to include 0, and I'm going to include 2, which means we ignore everything else, right? I'm going to ignore everything outside of that interval. Okay, now what? Well, now we still have a minimum. That minimum is the same. 0 is still lower than every other point on the graph. And is there a point that's higher? Well, remember, we don't have this arrow anymore, right? Because we're stopping here. So for this domain, 4 is going to be the maximum because every other point on the graph is below or has a y-coordinate lower than 4. Okay, so how about the next one? Well, I didn't change the endpoint, the right endpoint, right? It's still 2. So this is still going to have a maximum at 4, but now I changed it to an open interval. That's not an open interval. The end is open, right? It doesn't contain that left-hand endpoint. Okay, let's think about this, right? You need to think about this for a second on your own and see what you come up with here. Hopefully you see there is no minimum, right? N-A, no minimum. And here you can kind of think through this. Pick a number that you have that you're going to call your candidate to be the minimum. Well, I'm going to go a little further to the left, and there's always this is the trick with open intervals. There's always going to be a little bit further I can go. If you pick x equals 0.00001 and you're hoping that f of 0.00001 is the minimum, it's not, because I'm going to look at I need another letter. I'm going to look at t equals 0.0000001. That value, the y value of that point, of that number, is lower than the y value of your point. So your point was not actually the minimum. Now you can continue this indefinitely. No matter how small a number you pick, there's always going to be, you can go a little bit closer to 0, and that's going to mess you up. All right, so how about the next one? 0 and 2, and now I'm not going to include that right-hand endpoint either. Right? I'm going to take this out. So that's not a filled-in circle anymore. It's an open circle. And now what? Well, now I have the same problem on both ends. Right? There's still no minimum because I have the same problem at 0. And now I have the same problem at 2. Pick a number close to 2 to potentially be your maximum. Well, I can always pick something a little bit closer to 2 than your number, and that the y value for that number, that x value, is going to be a little bit higher. So your value will never be the maximum. So there's no maximum here either. So we see that all of the possibilities can happen. It's possible to have both an absolute maximum and an absolute minimum. We can have one or the other, and we can have none at all. So in situations like this, the next question the mathematicians like to ask is, okay, how can I tell? How can I tell when I can be sure these things are going to exist? All right, and here's how. We have a little theorem, the extreme value theorem. It says a function that's continuous. Okay, I want to stop there for a second. Remember, back when we talked about continuity, I said we're going to be referencing continuity throughout the rest of the class. Continuous functions, in a certain sense, are good functions. They're well-behaved functions. They're going to have a lot of the properties that we want to talk about. All right, so that's what we're talking about here. If we have a function and it's continuous, right, specifically on a closed interval, a and b, where a and b are numbers. So no fair putting infinity in there for one of those, right? It has to be kind of a bounded interval. Then f will have both an absolute maximum and an absolute minimum on the interval. Now, and I want to be clear, because this is people get a little tricky with math theorems. They don't read both ways, right? This isn't saying that functions that are discontinuous can't have absolute maximum and minimum values. They can. And this isn't saying that functions that are continuous on open intervals can't have maximum and minimum values. They can. All this is saying is the only time I can be certain that this absolute maximum and this absolute minimum will exist 100% of the time is when we have these conditions, when the function is continuous on a closed interval. All right, so now let's flash back. Right, these were our numbers from before, and I'm afraid I reversed the order here on you. The minimum, these are the minima, and these are the maxima. And look at what happened, right? The only interval where we had both was this one. That is the closed bounded interval, exactly like the theorem said, right? When we were just looking at a restricted domain that was a closed interval on which the function was continuous, just like the theorem guaranteed, we had both an absolute maximum and an absolute minimum. And just like I was talking on the last slide, it can happen that an absolute maximum and minimum occurs, right? Take this case. That's an unbounded interval, and we did have a minimum. It can happen in other situations. I just can't be guaranteed that it will. Okay, so that's absolute maximum and minimum. Well, we have another idea here that's a little less restrictive, but that's still going to be useful. It's called a local maximum and a local minima. Right? What this means is it's not the absolute highest point on the graph or lowest point on the graph, but if you look at the definition here, the number f of c is a local maximum if f of c is greater than f of x when x is near c, when x is in a neighborhood of c. All right, so take a look at my graph here, and I'm going to look at c equals 0. This point here looks like it's about 0,5. That point is a local maximum. It's not an absolute maximum. This point right here, for example, among others, is higher than it. So it can't qualify as an absolute one. It is, however, higher than all of the points in a neighborhood of 0. Right, so that's what we mean by a local maximum. And a local minimum works the same way. We're just going to switch this from less than or equal. So if you look over here at 3, this point here looks like 3, maybe negative 0.25. This point is lower than every point in this neighborhood. Therefore, it's a local minima, but it's not absolute, right? Because, I mean, this point here, for example, again, among others, is lower than that one. All right, so we have two types now. Absolute, just like the English word absolute, that is the absolute highest or lowest point. And then we have these local maximum and minimum. Those are just kind of higher or lower than everything around them. Okay, so those are our definitions, right? Those are our concepts. Now, in the next slide, we're going to hit the calculus bit, and we're going to see how we can use calculus to actually find the absolute maximum and the absolute minimum for a given function.